In the analysis of algorithms, when a function is obtained for an algorithm, big O of this function is not typically derived by applying the basic definition. However, it is derived by applying a group of simplification rules for big O. To some functions, it is too complicated to apply the basic definition to get the witnesses. As a result, following these simplification rules of big O, especially on a commonly known functions, will make deriving big O easy and straightforward. The first rule is called the sum rule. In this rule, it says that if you have a function f of x that is a sum of several terms, to find big O of f of x, simply keep the one with the largest growth rate and omit all other terms. Mathematically, we can write it as follows. If we have a function f of 1 that is of order g1, and we have f of 2 of order g2, then to find the order of the summation of these functions, it is equal to the order of the maximum of their corresponding orders g1 and g2. But how to find the maximum between the two functions g1 and g2? To find the maximum between the two functions g1 and g2, we use infinite limits. So let limit as x goes to infinity between g1x over g2x equal to a. Now it depends on the value of a. If a is equal to 0, then that means g2 grows faster and g2 is the largest. And if a is equal to infinity, then g1 grows faster and it is the largest and it's equal to the maximum. So here we write if a is equal to 0, then g2 grows faster and maximum between g1 of x and g2 of x will be equal to g2. And if a is equal to infinity, then g1 grows faster and it's going to be the larger. And then we say the maximum and maximum of g1 of x and g2 of x will be equal to g1. The sum rule is not only applicable on big O, it is also applicable on big theta. The second simplification rule, it's a special case of the sum rule. If we have a function f1 and f2, and both are of order g, so it is different little bit than the sum rule, because in the sum rule, f1 and f2 have different orders. But f1 and f2 in this rule have the same order, and it is a special case of the sum rule. Then it says that the order of the summation is the order of one of them because both belong to the same order. The third rule, it's called the product rule. It says if we have a product of several factors, then first you ignore the constants, and then the order will be the multiplication of these factors. This is how it is written mathematically. F of 1 belongs to order of g1 and f2 belongs to order of g2. If we want to find the order of the product of f1 and f2, then it's equal to the order of the product of their corresponding orders, g1 and g2. In this example, we want to give a big O estimate for the following function. This function consists of the addition of two parts. In the first part, it is a 3n multiplied by log n factorial, and the second part is a polynomial n squared plus 3 multiplied by log n. Now, we need to find the order of each part of this function, and then we will use the simplification rules of big O to combine all these orders to get to the final big O for this function. For 3n, we know that it belongs to big O of n because it's a polynomial. And for n squared plus 3, we know it belongs to big O of n squared because it's also a polynomial. And for log n, it belongs to big O of itself. But for log n factorial, we need to simplify it and see it belongs to which big O. So let's work on log n factorial first. You know that n factorial, it can be written as a product of n multiplied by n minus 1 until multiplied by 1. Now use the log property on a product of numbers, then it will be equal to log n plus log n minus 1 plus log n minus 2 until plus log 1. Now when you replace every log by log n, so keep log n, but log n minus 1, replace it by log n, and all the way until the end, replace every term by log n. Then log n factorial will be in fact less than or equal to the summation of log n times, because when you add these log n, they are repeated n times, the answer will be n log n. If you consider this inequality, log n factorial less than or equal to n log n, then this is actually the basic definition for big O between log n factorial and n log n. To find the witness or the witnesses, the number that is in front of n log n will be c, and the value of k is equal to 1. So therefore here we can conclude that log n factorial belongs to big O of n log n. Now let's go for this part first of the function and find the order of these individual parts together. First, we have a 3n belongs to big O of n. According to the polynomial theorem, 3n belongs to big theta of n, and since it belongs to big theta of n, then it belongs to big O. And also we have a proof that log n factorial belongs to big O of n log n. Now using the product rule, to find the order of the product between these two functions, then we multiply the order of each of them to get the answer. So the answer will be order of n multiplied by n log n, and the answer is n squared log n. For the second part, the polynomial n squared plus 3 belongs to big O of n squared according to the polynomial theorem. Why? Because n squared plus 3 belongs to big theta of n squared, and therefore it belongs to big O of n squared. And since n squared plus 3 belongs to big O of n squared, and log n belongs to big O of itself, then according to the product rule, n squared plus 3 multiplied by log n, which is this part, the order is equal to the product of their corresponding order. So you multiply n squared by log n, and you will get the order for this product is n squared log n. Notice for this part we have found order n squared log n, and for the second part we have obtained the same order. So according to the sum rule, we can take one of those orders as the answer. So therefore we can conclude that this function belongs to big O of n squared log n. For the other example, we want to give big O estimate for this function. This function consists of the addition of two parts. In the first part, we have x plus 1 multiplied by log x squared plus 1. And the second part is 3x squared. Now we need to find big O of x plus 1, big O of log of x squared plus 1, and log and big O of a 3x squared, and then we use the simplification rule for big O to combine all orders of these functions into one order as the final answer. So let's go for x plus 1 first. x1 belongs to big O of x according to the polynomial rule. Next is log x squared plus 1. Now we need to simplify it. So we will replace 1 by x squared, and we add the two x squares, we will get log 2x squared. Apply the log property over the product of two numbers, we will get log 2 plus 2 log x. Now again, replace log 2 by log x. So when you replace log 2 by log x, then this equation will be less than or equal to log x plus 2 log x. You add log x, you will get 3 log x. But here notice, when you do the replacement for log 2 by log x, then x will not be greater than or equal to 1. It should be greater than or equal to 2, because this relation will be true only after x is greater than or equal to 2. So according to the basic definition, we have this equation less than or equal to this equation. So c is 3, log x is the g of x for the basic definition, and k will be equal to 2. And from here we can conclude that log of x squared plus 1 belongs to big O of log of x. Actually, log for any polynomial of any power is always order of log of x, and you can prove this by using limits as well. So the witness is c is 3 and k is equal to 2. From a and b, we are considering this part. We found big O of this equation and big O of this equation. So according to the product rule, we multiply the orders of these two functions. So we multiply the order of x plus 1 and log x2 plus 1, and it will be x log x. Now for 3x squared, according to the polynomial theorem, it belongs to x squared. So this one belongs to x squared, and this one belongs to x log x. And to find the order of the sum of these two parts, we use the sum rule. In the sum rule, since we found the order of this part x log x, and we found the order of this part 3x squared, so the order of the summation will be equal to the order of the maximum between these two functions. To find the maximum between these two functions, we use infinite limit. So we divide x log x over x squared, divide both sides by x, you will get log x over x. When x goes to infinity, log x is infinity and x is infinity. So we have infinity over infinity, so we can apply L'Hopital's rule. Take derivative of log x and derivative of x. Then you will have, because we will convert it into len, so we will have a constant multiplied by len, and the derivative of len is 1 over n, and the derivative of x is 1. So finally we will have limit as x goes to infinity 1 over x. And limit when x goes to infinity 1 over x is 0, so the answer is 0. Since we have a limit for x log x and x squared is equal to 0, then x squared grows faster and the maximum will be equal to x squared. So therefore, we say that f of x belongs to O of x squared. In the third example, we need to find an efficiency class for each of the following functions. When we say efficiency class, it means the class of the function that this expression or function belongs to. In fact, the classes available, commonly classes, are polynomial, logarithm, exponential, end log n, and etc. So for these functions, we would like to know what is the class that each of these functions belongs to. You can find the answer verbally by looking at these two. It consists of a combination of two functions. The one is a constant, the other one is n log n. So the order for n log n is n log n, and for constant it is 3. So how to find which part grows faster? We apply sum rule. And according to the sum rule, it will be equal to n log n, so it belongs to n log n class. Now for 3n raised to power 3, this is a polynomial of degree 3, so it belongs to big O of n raised to power 3. And for the other part, we have already proved that for any power of log, it is always belongs to big O of n. So here we have big O of n raised to power 3, and here we have order of n, and using summation rule we will find that n raised to power 3 grows faster, so it belongs to a polynomial of degree 3 class. So the class, the efficiency class, is a polynomial. As an exercise, I have provided 2 questions. And the first question, it is asking for which function grows faster. So you need to apply infinite limits and look at the answer. If it is equal to 0, when you divide fn over gn, if it is equal to 0, so this one grows faster, and if the answer is equal to infinity, then this function grows faster. Finally, we want you to show that this function is big O of the gn function, but not the reverse. And also in this example, to find the answer, you can use infinite limits.